Okay, this question says for gaseous state, if the most probable speed is denoted by C star and average speed by C bar and root mean square speed by C, then for a large number of molecules, the ratio of these speeds are pretty standard and straightforward question, right? So what do we know about this C star that they have said? C star is the most probable speed. What is most probable speed? C star is going to be equal to root 2 RT by M, right? And 2 R the universal gas constant, T is temperature in Kelvin, and M is molar mass in kg. Similarly, C bar, average velocity, can be written as root of 8 RT by pi M. And if you are looking at URMS, C, that is root 3 RT by M, right? So if I take ratio of these, you can see this is the smallest, right? RT by M is there in all of them. So root 2 is to root 8 by pi is to 3, right? 8 by pi will be 8 by 3.14 will be like between 2 and 3, right? So yeah, what we are going to get is root 2 is to root 8 by pi. If I take ratio of these is to root 3, right? Let's see if there is something that looks like this, right? So yeah, obviously the one that is the smallest has to be our C star, right? So it has to be 1, and everything else can be represented as a ratio of that C star, right? So for that, what will I do? I'll divide throughout by root 2, right? So I'm going to put a 2 here and I'm going to put a 2 here, right? So root 2 by root 2 is obviously 1, and 1 is to root 4 by pi, right? So 4 by pi would be how much? I mean, 16 by 4 pi. 4 pi is roughly 100 by 8, right? 4 pi, yeah, 12.56 is 100 by 8. So 8 goes to the numerator. So 16 into 8 by 100. 16, 80, 48, 128, 1.28. Roughly, this is root of 1.28. Now, what can I say about root of 1.28? The root of 1.21 would have been exactly 1.1. So this is slightly greater than 1.1. Now we have root of 3 by 2, which is root of 1.5. What can I say about root of 1.5? 12 square is 12 square is 144. So 1.2 square is 1.44. So obviously this has to be slightly greater than 1.2. Let's see. So I'm looking at 1 is to 1 point something and 1.2 something, right? So 1.128 and 1.225. This looks perfectly fine to me. So yeah, what is the ratio of these three? It's obviously option C. Okay, this question says, use the following data to calculate the second electron affinity of oxygen, right? So we need O minus. I mean, we know what is second affinity of oxygen atom. It will be when you are adding that second electron, right? So when you have added one electron, you already have O minus. Now on top of that, you are adding one more electron to get O2 minus. Obviously, this is an endothermic process. We have studied about this. All second electron affinity onwards would be negative, or second electron gain enthalpy onwards would be positive. Why? Because you have to supply energy to push that electron into an already negative anion, right? So yeah, this is the process for which we have to find the electron affinity. We'll see. I mean, yeah, electron gain enthalpy is probably what is expected, because electron affinity would be negative, right? So let's see, let's look at the options here. All the options are positive, right? So yeah, this is second electron gain enthalpy that we are interested in. Now let's see, the heat of sublimation of magnesium is given to us as 147.7 kilojoule per mole. Ionization energy of magnesium to form Mg2 plus, I mean the combined IE1 plus IE2 combined is given to us as 2189 kilojoule per mole, and bond dissociation energy for oxygen is given as 498.4. First electron affinity is given as minus 141 kilojoule per mole, right? First electron, when you are adding, some amount of energy is released. So first electron gain enthalpy would be negative, and it is minus 141. Heat of formation of MgO, right? Solid is given to us as minus 601.7 kilojoule per mole, and lattice energy of MgO when there is lattice formation, right? So looking at the negative sign, we can understand this is about the lattice formation enthalpy that is given minus 3791 kilojoule per mole. Or if you have to break down Mg, 1 mole of MgO into Mg plus Mg2 plus and O2 minus, the in gaseous phase the energy required will be 3791. Obviously this question is an application of our Born-Haber cycle. So let's see, what do we have? The formation of MgO. If I can write Mg solid plus half O2 in gas phase, giving you MgO solid. This should have been the reaction, net reaction that is taking place, right? Now, if I look at this, first of all, we need sublimation, right? So, sublimation of magnesium is given as 147.7. So, on giving 147.7 kilojoule, this will convert into Mg in gas phase. Now, what do we need? The two ionization energy I have to give, right? So, the combined ionization energy giving us Mg2 plus in gas phase is given to us as 2189 kilojoule, right? 2189 kilojoule per mole. Now, when I'm looking at bond dissociation, as far as oxygen bond dissociation is concerned, bond dissociation energy is 498.4 kilojoule per mole, but only have half mole, right? So half of 498.4 divided by 2 will convert this into 1 mole of oxygen gas, right? Half mole of oxygen was dissociating. 1 mole we need 498.4, half mole we only need half of that, right? Now, after this, first it converts into O minus in gas, in which we know minus 141 kilojoule, right? First electron gain enthalpy is what we are speaking about here. Yeah. Then after that, I am converting it into O2 minus. Now this is exactly what is asked. The enthalpy change associated with this process is what is asked. Now, if Mg2 plus and O2 minus is allowed to convert into Mg solid, we know 3791 kilojoule per mole will be released. And that's it, right? Now, the net reaction, one single short reaction, if I had Mg plus half O2 giving MgO, if this reaction were to happen, that enthalpy would have been what we call enthalpy of formation, which is given to us as minus 601.7 kilojoule per mole. Right. So what do we know? We know that as far as enthalpy is concerned, it's a state function. So irrespective of how you go from one to another, the total enthalpy change should be same, right? Or we can speak in terms of Hess's law. We can say that if you do it in a single step or in multiple steps, it doesn't matter. The net enthalpy change should be same in both of them. So sum of all of these individual enthalpies should be equal to the direct step enthalpy. This is the idea. Right. So what can we write? Okay, minus 601.7, the total net enthalpy, direct one. All of these are in kilojoule only, so I don't want to write it. It's unnecessary burden to keep you writing the units, right? So 147.7 plus 498.4 divided by 2. 500 by 2 would have been 250. This is what? 1.6 less. So 0.8 less of 250 is what? 249.2. Then we have 2189. Then we have 141 with a minus sign. I mean, basically it is the first electron gain enthalpy, which is negative 141. Then we had what? Question mark, right? So plus what we need. Let's call it as X. Then minus 3791. This is what we are seeing. So from here we can see that X will be equal to how much? 3791 minus 601.7 minus 147.7 minus 249.2 minus 2189 minus 141. Oh no, plus 141. Right, this will be the value of your X which we need. This is the final answer, right? So 3791 minus 2189 is how much? 89. If I reduce, it's 2, right? So 3702, 100 more to 3602. Then you have 1602, right? So 1602 minus 601.7, right? I'm inclined to directly do this calculation here, right? So 0.7 minus 249.2 plus 141, right? So this you can see is almost 602 only, right? Just 0.3 short. So 1000.3 minus what is this? 147.7 plus 0.2 is 147.9. Wait, what? If I bring it here, in fact, this 0.7 here, it will be almost 250, right? 250 plus 147. 250 plus 147 is 350, 397, 396.9, right? So minus 396.9. Yeah, plus 141. Right, so this is how much? Minus Okay, maybe I should have even cancelled these out. Minus 147 and plus 150, 141, and this would have given me how much? Minus 6.7 left, right? So yeah, 6.7, and that means 1000 minus 6.7 and 249.2, 249.9 plus 6, so 255.9. Somewhere in this range. I'm not even concerned about the exact value. Let's see. Let's look at the options. Yeah, they are decently far away from each other. 600, 740, 1300 and 140, right? So let's see. Looking at this, what do I see? This is somewhere around 250. This is somewhere around 1000. So somewhere around 750 is what I'm expecting here, right? Even, in fact, even what? 5.6 less than 750. 740, 743, somewhere around this is what I'm seeing here, right? So yeah, 744.4 looks perfectly fine to me. So idea is that you're almost never required to do the exact calculation. Just go through the options. If they're decently far separated from each other, don't do exact calculations. Just even mental mathematics will be more than sufficient, right? Yeah, so what I'm seeing here is that correct answer is of course option B. Okay, this question says find the use the following data to calculate the lattice energy of cesium oxide. Obviously, Born-Haber cycle is probably what is expected. Enthalpy of formation of cesium oxide is given to us. Enthalpy of sublimation of cesium is given to us. First ionization energy of cesium is given to us. Enthalpy of dissociation of O2 gas is given to us into O2 molecules, right? First electron affinity of oxygen is given to us, and second electron affinity of oxygen is also given to us. Based on this data, we need to find out, right? We need to find out the yeah, so what do we do here? Obviously, Born-Haber cycle, we need to find out the lattice energy, right? So this is the typical thing. So what do? We are saying, okay, I need cesium oxide finally, right? What is cesium oxide? Cesium is the first group, right? So CS2O is what we are going to get. So if I want to get CS2O, 1 mole of CS2, enthalpy of formation is enthalpy change when 1 mole of the substance is made from its constituent elements, required amount of constituent elements in their standard states. So 2C S in its solid form, right? 2 cesium in solid form plus half O2 giving you CS2O, right? Just like you have your Na2O, right? Just like the K2O, first group oxide, right? So yeah, this is the net reaction that you can think of. Here, what is given is that the enthalpy of formation of cesium oxide is given as minus 233. Is this value in kilojoule per mole? So yeah, all of them are in kilojoule per mole. Life is sorted. Minus 233 kilojoule per mole. I'm not even going to write 233 kilojoule anymore, right? So first I'll convert this into 2CS in gas phase, for which what is the energy that is required? For the sublimation of cesium, 78 kilojoule per mole is required, but I'm converting it in 2 moles of cesium, right? So 2 into 78, 156 kilojoule will be absorbed here. After that, I have to convert this into 2CS plus in gas phase, right? So cesium, first ionization energy is given to us as 375 kilojoule per mole, but that is for obviously 1 mole. We have 2 moles, so 375 into 2 is how much? 750, yeah? So 750 kilojoule is what you need here. Now, first of all, this is converted into 1 mole of oxygen gas. Half of bond dissociation energy is what is going to be required, right? So enthalpy of dissociation of oxygen molecules is given as 494 kilojoule per mole, but we only have half mole. So 494 divided by 2, right? So what is that? 494 divided by 2 is 247, right? So 247 kilojoule will be involved here. Then after that, I'm converting this into O minus, and then I'm converting this into O2 minus, right? So what am I going to get? O2 minus is where is the first time? Yeah, so minus 141 kilojoule per mole is the first electron gain enthalpy. So here it is minus 141, and in the second step it is an endothermic, plus 845 is what is required here, right? Now after this we are looking at lattice energy of cesium is what cesium oxide is what we are trying to find out. The lattice formation energy more like is what we are trying to find out here. What is going to happen here after this? 2Cs plus and O2 minus will convert into CS2O. The energy released here is what we, enthalpy change here is what we are calling as lattice energy. So we are going to say that okay here plus Le, right? So plus Le is going to, technically speaking, at places you might also even come across lattice energy as the energy required to break down 1 mole of the ionic solid into its gaseous separated ions. That angle is also there, to be honest. So yeah, looking at the but yeah, by definition what we have in syllabus is lattice energy is the energy required to break down 1 mole of ionic substance into its separated gaseous ions. So you can see here plus minus and all of these tricks are being done here. Let's see, right? So how does that affect us? Basically I have to write this as minus lattice energy, right? Why? Because converting CH2O to separated ions is what you call as lattice energy. So reverse process will be minus of lattice energy. Anyways, we know lattice energy is energy required to break the bonds, so it has to be positive, it can't be negative, right? So anyways, there are 3 negative answers and 1 positive answer, so obviously it has to be this. But let's see, right? So what do we do? Born-Haber cycle, we say that okay, minus 233 should be equal to the single step enthalpy of formation should be equal to the sum of individual energies. So 156 plus 247 plus 750 plus yeah, that's it, 750 minus, yeah, plus 845 minus 141 minus lattice energy, right? This should be it. If I take lattice energy to the other side, I'm going to get lattice energy to be equal to how much? Le will be equal to, let's see. So this will go to the other side. This minus 233 will come to this side. So 233 plus 156 plus 247, right? So 247 plus 233, 250, 280, 480. 480 plus 156 is 580, 580, 636. So these 3 are taken care of so far. 636 plus 845 plus 750, right? So 750 plus 750 is 1500, 1500, and then 145 is there, minus 141 means 4, right? So 4. Yeah, so this is what I am getting, right? On adding these two, what do I get? So 10, 1. Yeah, right? Did I make a mistake somewhere around here? 750 plus 750 would have been, oh yeah, 95 should have been there, right? So 750 plus 750 is 1500. Then 95 minus 141 is what was there. So 95 minus 141, 141 minus yeah, 95 minus 141. 141 minus 95 is how much? 41 plus 5, 46, right? So minus 46 will also be here. Minus 46 means 590 plus 1500. This is what I'm getting. 0, 9, 10, 1, 2090, right? So 2090 is going to be the lattice energy here. Obviously, it had to be B, but yeah, whatever. So our correct answer is B option. Okay, this is a very simple question. The number of unpaired electrons in Mn4 plus is what is asked. Obviously, atomic number is given as 25. I hope you don't need this anymore. So yeah, what do we have? Manganese, we need 4 plus, right? So manganese, originally atomic number 25 would mean that you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. This is how it normally will be, right? So again, I mean, it's up to you if you want to write this whole thingy as AR, atomic number 18 till 18, you can write like this, then 4s2, 3d5, that's up to you. Then after that, we need to make Mn4 plus. First, electron is removed from the outermost shell, which is 4th shell. So first, these 2 electrons will be removed. Then after that, from your 3d5, 2 more electrons are to be removed. So we will end up getting 3d3, which means that there is only one shell which has like, or subshell rather, which has unpaired electrons, which is your 3d subshell. Number of unpaired electrons is how much? You can see 3d3 would mean that there are 3 unpaired electrons. So final answer is D option. Okay, this is straightforward question. Which of the following is an ionic compound, right? So how do you determine whether a bond between two elements will be ionic or not? You can use electronegativity difference, right? So we say that an electronegativity difference delta x of about greater than 1.7, right? There's no exact value which we say, okay, this means that this is definitely ionic. Nothing like this. It's just an empirical one. There is also your percentage ionic character in a covalent bond formula, based on which also you can speak of I'm sure you might have come across this 3.5 delta plus 16 delta plus 3.5 delta square, right? So where delta is the electronegativity difference between the two elements that are covalently bonded, this gives you the percentage ionic character, right? So percentage ionic character, more is the delta, more will be the percentage ionic character. Based on this, if we calculate somewhere around 2 electronegativity difference would mean that the substance will be more ionic than covalent. When I'm looking at sulfur and oxygen, sulfur is 2.5, oxygen is 3.5 in your Pauling scale. Electronegativity difference is not much. You would obviously expect this to be covalent, right? ICl, same story, right? So iodine is what, 2.5, chlorine is 3, bromine is 2.8, ICl, you would obviously expect it to be covalent. When I'm looking at potassium and iodine, potassium is like around 0.9, right? Somewhere around 0.9. 0.9 and iodine is around 2.5. So the difference we are seeing somewhere around 1.6. Okay, this is a very close to your 1.7. So that's why I'm saying it's not like an exact thing that, you know, okay, anything below 1.7 would mean that this is covalently bonded. No, it's just that, yeah, if you look at the electronegativity difference, there is a significant electronegativity difference that should be sufficient to tell us that this is mostly going to be ionic, right? So when you have your CHCl3, right, so you have your chlorine which is attached to your carbon. Chlorine has electronegativity of 3 and carbon has electronegativity of 2.5. So you can say, okay, again covalent only, right? Polar, somewhat polar, but yeah, still covalent, right? Yeah, one more way is to think that ionic substances would mean that you have a cation and an anion. Cation would mean that you would have a metal which has this tendency to form cation by losing electrons. If you look at all of these, you can see iodine, chlorine, sulfur, oxygen, carbon, hydrogen, chlorine, all of these are non-metals. No chance that you would get a cation, right? So there is only one thing where there is a possibility at least of this being ionic, that is obviously option C, which is our final answer.